Look up at the night sky. What do you see? A scattering of stars, perhaps a planet or two, the gentle glow of the Milky Way. But what you're really looking at is only a fraction of reality. In fact, everything we can see, every star, every galaxy, every speck of cosmic dust, makes up less than 5% of the universe. The rest is hidden in plain sight, woven into the very fabric of space itself by something we call the dark matter web. Think about that for a moment. The grand cosmic stage, with its swirling galaxies and glittering clusters, is merely the visible embroidery on an invisible tapestry, one whose threads we cannot see, whose patterns we can only infer, yet which dictates the structure and fate of the entire cosmos. This is the greatest detective story in the history of science, and you are part of it. For decades, astronomers and physicists have been piecing together clues, tracing the ghostly outlines of something that refuses to be seen, an architecture built from matter that doesn't emit, absorb, or reflect light. It doesn't interact with the electromagnetic force, yet its gravitational pull is so immense that it bends light, twists spacetime, and sculpts the universe on the largest scales. We are surrounded by it, even passing through it unnoticed every second, and yet it remains one of the most profound and elusive puzzles of our time. What is it made of? How did it form? Why does it cling to the edges of our understanding, taunting us with its silence? Today, we're going to explore 25 of the most compelling mysteries tied to this cosmic enigma. From the faint filaments of dark matter that connect galaxies like threads in a web, to the vast, empty voids where it seems to retreat altogether, each mystery is a doorway into a deeper layer of reality. We'll venture into realms where physics as we know it begins to fray, where dark matter's secrets challenge not just what we see, but how we think. This isn't just a tour of the unknown. It's an invitation to wonder, to question, and to imagine alongside those at the very frontier of human knowledge. So settle in, open your mind, and let's begin. To understand this grand invisible architecture, we must first reimagine the universe, not as a collection of isolated islands, but as a single, interconnected metropolis. The cosmic web is its blueprint. Picture the largest structure you can, a mountain range, perhaps, or an ocean. Now, magnify that to an almost unimaginable scale, a sprawling network of dark matter filaments that stretches across billions of light years, connecting immense galaxy clusters at its dense intersections and surrounding vast, empty voids. This is the cosmic web. It is the fundamental skeleton upon which the visible universe is built. The story of its discovery begins not with a sudden glimpse, but with a growing unease among astronomers. For centuries, we mapped the heavens by the light we could see, but in the 1970s and 80s, scientists like Vera Rubin were studying the rotation of galaxies and found something deeply puzzling. The stars at the outer edges of galaxies were moving far too quickly. According to the laws of gravity and the amount of visible matter, these stars should have been flung off into the void, like children flying off a merry-go-round, spinning too fast. The only explanation was that the galaxies were surrounded by a massive, invisible halo of something, a substance that provided the extra gravitational glue to hold everything together. This was our first major clue to dark matter's existence, but the plot thickened as our telescopes grew more powerful, allowing us to map the universe in 3 dimensions. A pattern began to emerge from the cosmic census of galaxy positions. Instead of being scattered randomly, galaxies were arranged in a way that defied chance. They lined up along vast, thread-like structures, gathering in huge clusters at the points where these threads intersected. It was like looking down on a city at night and seeing the streetlights trace out the roads and intersections of a map you couldn't otherwise see. The light revealed the pattern, but the road itself was dark. This is where gravity becomes our guide. We cannot see the dark matter, but we can see its profound gravitational effects. It acts as the ultimate cosmic sculptor. Think of the universe just after the Big Bang. It wasn't perfectly smooth. It had tiny, random fluctuations in density. Those minuscule wrinkles in spacetime were the seeds of destiny. Over billions of years, gravity tirelessly worked on those seeds. Regions with slightly more dark matter had a stronger gravitational pull, drawing in more and more matter from their surroundings. This process amplified the initial wrinkles, pulling dark matter into an interconnected system of sheets and filaments, and leaving behind the enormous, empty cosmic voids. The most compelling evidence for this web comes from a phenomenon called gravitational lensing. The immense mass of these dark matter filaments warps the fabric of spacetime itself, bending the path of light from galaxies far behind them. It's as if we're looking at a distant street lamp. Through the heat haze rising from a hot road, the image is distorted. By meticulously mapping these subtle distortions in the light of millions of galaxies, astronomers can trace the invisible mass causing them, literally drawing a map of the dark matter web. We are, in a very real sense, seeing the silhouette of the invisible. So, the first great mystery is not just that the cosmic web exists, but what its intricate structure reveals about the laws of physics themselves. Its delicate filamentary patterns are a fossil record, preserving the conditions of the infant universe and the relentless pull of gravity across eons. It is an architecture built from a material we cannot touch, see, or fully comprehend, yet it is the very framework that holds our reality together, and it all begins with the faintest whisper of gravity in the dark. This gravitational glue, this unseen anchor holding galaxies together, was the first monumental clue. But to truly prove the existence of something you cannot see, you need more than just a theory about spinning galaxies. You need to catch it in the act, to witness its shadow, and that is precisely what the next major piece of the puzzle allowed us to do. It's a phenomenon that turns the entire universe into a natural laboratory, using one of nature's most fundamental tools, light itself. We call it gravitational lensing. The concept is a breathtaking consequence of Einstein's theory of general relativity. It proposes that mass doesn't just create gravity, it warps the very fabric of space and time around it. Imagine placing a heavy bowling ball in the center of a taut rubber sheet. The sheet dips and curves. Now, roll a marble across that curved surface. Its path will bend, following the contour created by the bowling ball. In the cosmos, the bowling ball is a massive object like a galaxy cluster, and the marble is a beam of light traveling from a distant galaxy. The invisible mass of dark matter within that cluster creates a profound curvature in spacetime, bending the light's path as it travels toward us. It's a cosmic illusionist's trick, where the background reality is distorted by an unseen foreground force. This bending of light creates extraordinary effects. Sometimes, a single distant galaxy can appear to us as multiple, distorted images arranged in a circle or an arc around the closer, lensing cluster, an effect known as an Einstein ring. Other times, the light is simply smeared and stretched, making distant galaxies look like faint, ethereal streaks across the sky. For astronomers, this isn't a nuisance, it's a gift. By meticulously measuring the precise way this background light is distorted, they can work backwards. They can calculate the exact amount of mass in the foreground cluster that was required to cause that specific warping. It's a method of cosmic cartography that allows us to literally map the distribution of mass, including the dominant, invisible dark matter component. We are drawing a picture of the invisible by studying the distortions in the visible. Perhaps no single observation demonstrates the power of this technique more dramatically than the bullet cluster. This is not a single galaxy, but two entire clusters of galaxies that have violently collided with one another. This event provided a crucial natural experiment. a way to separate the different components of the universe and see how they behave. Think of it like this. During the collision, the clouds of hot gas within each cluster, the normal, visible matter, slammed into each other. The friction and pressure caused this gas to heat up and slow down, like two clouds of smoke colliding and mingling. Meanwhile, the vast clouds of dark matter, which does not interact with anything except through gravity, passed right through the collision unaffected. They were like two ghostly shadows passing through one another without a sound. When astronomers used gravitational lensing to map the total mass distribution after the collision, they found something astonishing. The majority of the mass, the gravitational core of the system, was not where the visible gas was located. It was in two separate blobs, far out in front of the gas, exactly where the dark matter from each cluster would have sailed through unimpeded. This observation was a monumental blow to alternative theories that tried to explain the missing mass by modifying the laws of gravity itself. Modified gravity would have predicted that the gravitational effect should be strongest where the most visible matter is, the gas. But the lensing map showed the gravity was somewhere else entirely, proving that the extra mass is a real physical substance that behaves differently from normal matter. The bullet cluster gave dark matter a physical reality. It wasn't just a mathematical fix anymore. It was a thing, with its own location and properties, waiting for us to finally understand it. The evidence for dark matter's existence, from galaxy rotations to the cosmic web itself, is overwhelming, but this only deepens the central, haunting question: what is it? We know it has mass and feels gravity, but it shuns light and ignores the electromagnetic force that lets us see and touch everything else. It's as if we've discovered a new, fundamental ingredient of the universe, but we can only detect it by the empty space it leaves in the recipe. For decades, physicists have been searching for the identity of this ghostly substance, and their investigations have led them down a fascinating, and at times frustrating, path. The leading theoretical candidate for this enigmatic material is a class of particles known as WIMP, or weakly interacting massive particles. The name itself is a perfect description. They are thought to be heavy, much heavier than a proton, and they interact so weakly with normal matter that trillions of them could be passing through your body every second without a single collision. But the appeal of WIMP goes far deeper than just a clever acronym. They represent what physicists call a beautiful solution, an idea that elegantly solves multiple profound puzzles at once. This elegance is rooted in a concept known as supersymmetry, a theoretical extension of the standard model of particle physics. Supersymmetry proposes that every known particle has a heavier superpartner twin. Many of these hypothesized superpartners would be stable, electrically neutral, and would only interact through gravity and the weak nuclear force, making them perfect candidates for WIMP. What makes this idea so compelling is the WIMP miracle, when physicists calculated how many of these particles would have been created in the seething heat of the Big Bang and then annihilated as the universe cooled. The predicted leftover abundance aligned almost perfectly with the amount of dark matter we observe shaping the cosmos today. It was a stunning coincidence that suggested the universe might be giving us a massive hint, pointing to a particle that not only solves the dark matter problem, but also helps unify the fundamental forces of nature. However, the universe is also a place of immense complexity, and WIMP are not the only actors auditioning for the role of dark matter. Another compelling candidate is the action, a hypothetical particle originally proposed to solve a completely different problem in quantum physics. Actions would be incredibly light, billions of times lighter than an electron, and would behave more like a pervasive, wave-like field throughout space. Then there are sterile neutrinos, heavier, more elusive cousins to the standard neutrinos we know, which could also account for the missing mass. Each candidate paints a different picture of the early universe, and requires different methods to detect. This brings us to the great experimental silence, a mystery within the mystery. For over 30 years, scientists have built extraordinarily sensitive experiments deep underground to finally catch a WIMP. These detectors, shielded from cosmic rays in old mines and tunnels, are designed to feel the faintest whisper of a bump, the rare occasion when a WIMP might actually collide with the nucleus of a normal atom. Yet, despite their incredible sensitivity, these direct detection experiments have, so far, heard nothing. The profound stillness is both puzzling and illuminating. It tells us that if WIMP are out there, they interact even more weakly than we thought, or they are simply different from what our most elegant theories predicted. This absence of a signal is itself a powerful piece of data, forcing us to broaden our search and reconsider our assumptions about the true nature of the cosmos's hidden architect. This profound silence from deep underground laboratories is a humbling reminder that nature often defies our most elegant predictions, but our search for dark matter's identity isn't confined to these quiet caverns. It also plays out on a much grander scale in the virtual universe of supercomputer simulations. And it's here that we encounter our next pair of puzzles, two mysteries that arise not from what we can't find in a detector, but from a striking mismatch between what our theories predict we should see in the sky and what we actually observe. Cosmologists have built incredibly sophisticated models that simulate the evolution of the universe from its first moments to the present day. These simulations are guided by our best understanding of physics and the known properties of dark matter, particularly the cold, dark matter model, which suggests these particles moved slowly in the early universe. When we run these cosmic forecasts, they consistently produce a universe that looks very much like our own, complete with a vast cosmic web of filaments and clusters. But they also predict something very specific about our own galactic neighborhood. They tell us that a large galaxy like the Milky Way should be surrounded by a bustling swarm of thousands of smaller dark matter clumps, called subhalos. According to the math, gravity should have pulled these dense knots of dark matter into orbit around us, each one a potential seed for a small satellite galaxy. This is where the mystery begins. When astronomers point their telescopes at the halo of the Milky Way, they don't find thousands of dwarf galaxy companions. They find dozens. There is a glaring discrepancy between the vast population of dark matter subhalos predicted by the simulations and the comparatively tiny number of small, light-emitting galaxies we actually see. It's as if a detailed forecast predicted a bustling metropolis with thousands of buildings, but when we arrive, we only find a few dozen structures, with the rest of the plots of land appearing completely empty. This is known as the missing satellites problem, but the plot thickens with a related issue, often called the too big to fail problem. This one is even more curious. Among the few dwarf galaxies we have found orbiting the Milky Way, the very brightest and most massive ones should, according to the simulations, reside within the very largest and most massive dark matter subhalos. These subhalos are so dense and have such strong gravity that they are considered too big to fail, that they should have easily attracted enough gas and dust to form a multitude of stars and become bright, prominent galaxies. Yet, observations show that these particular dwarfs are far dimmer than they should be. It appears that these massive, powerful subhalos somehow failed to form many stars, leaving them strangely faint and difficult to detect. The simulation says they should be brilliant beacons. Reality shows us they are barely flickering candles. So, what is happening? Are our magnificent supercomputer simulations fundamentally wrong? Or is the answer even more fascinating? Many scientists now believe the simulations are likely correct about the dark matter itself, that those thousands of subhalos are indeed out there, blanketing our galaxy. The solution to the mystery may be that the vast majority of them are completely dark. They are made purely of dark matter, containing little to no normal matter to ever ignite into stars. They are invisible ghosts orbiting an invisible host, a hidden entourage for the Milky Way that we simply cannot see. What could prevent a massive clump of dark matter from forming stars? The answer might lie with the normal matter itself. We know that after the Big Bang, the first stars and galaxies formed in the deepest potential wells of dark matter. But this process was messy and violent. The intense radiation from the first massive stars and early galaxies could have heated the surrounding gas, preventing it from cooling and falling into the smaller subhalos, effectively starving them of the star-forming fuel they needed. Alternatively, supernova explosions might have blown the gas right out of these smaller gravitational wells. The result would be a universe filled with dark matter clumps that never got the chance to light up, forever hiding in plain sight, their immense gravitational presence betrayed only by their profound darkness. Resolving this tension is a major goal for the next generation of telescopes, which will peer deeper than ever into the faint outskirts of our galaxy, searching for the slightest trace of starlight, or confirming a universe far darker than we ever imagined. If those dark, starless subhalos represent the unseen architecture within our own galaxy, we must now turn our gaze to the grandest possible scale, to the opposite end of the cosmic spectrum, the great nothingness. The dark matter web is not merely a collection of dense knots and connecting threads. It is also defined by what is absent. Enormous, sprawling regions of near total emptiness, known as cosmic voids, make up the majority of the volume of the universe. These are not small pockets of empty space. They are vast, spherical-like realms that can span hundreds of millions of light years, where galaxies are few and far between, and the density of matter is a tiny fraction of the cosmic average. They are the bubbles in the cosmic foam. This presents us with a profound and beautiful contradiction. To understand it, we must look back in time to the universe's first light, the cosmic microwave background. This ancient afterglow, a snapshot of the universe when it was just 380,000 years old, reveals a cosmos that was almost, but not quite, perfectly smooth. The temperature variations across the entire sky are incredibly minute, fluctuating by barely 1 part in 100,000. It was a remarkably homogeneous infant universe, a nearly smooth sea of hot plasma. So how did we get from that primordial smoothness to the extravagant structure we see today, a universe of dense clusters, intricate filaments, and these immense empty voids? This is one of the central mysteries of cosmic evolution, and dark matter is the key actor in the drama. The tiny fluctuations in that early plasma were the seeds of all future structure. There were the regions where, by random chance, there was a tiny bit more dark matter, and because dark matter feels gravity, it began to pull. Over billions of years, gravity acted as nature's great sculptor, relentlessly amplifying these minor differences. The slightly denser regions pulled in more and more matter from their surroundings, growing ever denser, eventually collapsing to form galaxies and the massive clusters at the web's nodes. But for every action, there is an equal and opposite reaction. As matter was pulled into the filaments and clusters, it was simultaneously pulled out of the regions in between. The voids were not born empty, they were evacuated. They are the great underdensities, the cosmic countryside, whose material has been steadily drained away to supply the growth of the metropolitan galaxy clusters. The dark matter provided the gravitational blueprint for this entire process, guiding the flow of both itself and the normal matter. But the story of the voids doesn't end with their creation. A second, even more mysterious force has begun to dominate their evolution: dark energy. We think of dark energy as the force causing the overall expansion of the universe to accelerate. But its effects are not uniform. In the crowded, gravity-rich environments of galaxy clusters, the powerful gravitational pull of all that mass fights a fierce tug of war against dark energy's outward push. However, in the deep matter-poor voids, there is very little gravity to resist. Here, dark energy operates unimpeded. It acts not by pushing per se, but by causing the very spacetime within the void to expand faster than the cosmic average. The voids are not just empty, they are actively getting emptier, growing larger and more pronounced over time. We are living in a universe that is becoming increasingly foamy, with the voids expanding and the web of galaxies being stretched into an ever more tenuous network. The great cosmic voids are not passive holes. They are dynamic entities, their accelerating expansion a direct window into the mysterious force that appears to be shaping the ultimate fate of the entire cosmos. For centuries, our model of the cosmos was built on a fundamental assumption that on the largest scales, the universe is homogeneous and isotropic. This cosmological principle suggests that there is no special place or direction in the universe. It should look roughly the same everywhere. It's a comforting, orderly idea. But what if this cornerstone of modern cosmology is wrong? What if there is a direction, a mysterious pull from a realm beyond what we can see? This is the unsettling possibility raised by one of the most contentious discoveries in recent astronomy, a phenomenon known as the dark flow. The story begins with the most ancient light we can measure, the cosmic microwave background. This radiation bath fills the entire sky and serves as the perfect reference frame against which all motion can be measured. Our solar system moves relative to this background. Our galaxy moves, and even our local cluster of galaxies has a measurable velocity. All of this motion makes sense, governed by the gravitational pull of nearby massive structures like the Great Attractor. But in 2008, a team of astronomers studying the peculiar velocities of extremely distant galaxy clusters found something that defied all explanation. They discovered that hundreds of clusters, scattered across billions of light years, were all streaming at immense speeds toward the same patch of sky, a point near the constellations of Centaurus and Vela. It was as if a vast, unseen river of galaxies was flowing in concert toward an unknown destination. The sheer scale of this motion is what makes it so baffling. These clusters are so far apart that not even the gravitational pull from the largest known superclusters could possibly coordinate their movement. The only conceivable source for such a coherent pull on such an immense scale would have to lie beyond the observable horizon of our universe, a region of space from which light has not had enough time to reach us since the Big Bang. The implication is staggering: a massive, uneven distribution of matter existing in the unobservable universe, its immense gravitational tug reaching across the void to steer entire clusters of galaxies like leaves caught in a current. This is the dark flow, a potential glimpse into the architecture of the multiverse, or a flaw in our most basic understanding of gravity. The controversy remains fierce, with some scientists questioning the data analysis, while others see it as the first hint of a cosmos far larger and more mysterious than we ever dreamed. If the dark flow hints at a gravitational anomaly from beyond our horizon, then the next mystery delivers its evidence from within our own galaxy, in the form of high-energy particles raining down from space. Cosmic rays are atomic nuclei and subatomic particles, accelerated to nearly the speed of light by powerful astrophysical engines like supernova and neutron stars. For over a century, we've been studying this cosmic rain, but in 2008, the same year the dark flow was proposed, a spacecraft called Pamela detected something peculiar in this deluge, an unexpected overabundance of positrons. A positron is the antimatter counterpart to the electron. It has the same mass but a positive charge. While some positrons are produced by known objects like pulsars, the number detected by Pamela, and later confirmed by the Alpha Magnetic Spectrometer on the International Space Station, was far higher than standard astrophysical models could account for. The energy signature of these excess positrons was the real clue. As you go to higher and higher energies, the ratio of positrons to electrons increases in a very specific way. This precise energy spectrum is exactly what many theoretical physicists would expect to see if dark matter particles were annihilating with one another. Here's how that would work. Imagine two WIMP, the leading dark matter candidate, colliding in the dense heart of a galactic halo or within a filament of the cosmic web. According to Einstein's famous equation, their mass would be converted into pure energy, creating a spray of secondary particles, including electrons and positrons. These newly created particles would then travel across the galaxy, some eventually making their way to our detectors. The observed positron excess could be the long-sought indirect signature of dark matter revealing itself not through gravity, but through a violent act of self-destruction. It's a faint whisper of a signal, a ghostly echo of an invisible process happening in the darkness between the stars. Yet, the case remains open. Pulsars are also capable of producing positrons, and untangling their contribution from a potential dark matter signal is one of the great challenges in modern astrophysics. The answer, whatever it may be, is written in the energetic rain from the sky, a cryptic message we are still learning how to read. These high-energy cosmic messengers offer one potential window into dark matter's nature, but the most profound questions often demand we look at the universe itself as a whole, using its fundamental properties as our laboratory. This brings us to a pair of mysteries that strike at the very heart of modern cosmology, revealing cracks in our understanding that may very well be shaped by the invisible hand of dark matter. The first is known as the Hubble tension, and it represents nothing less than a full-blown crisis in our field. The Hubble constant is one of the most important numbers in all of cosmology. It's the rate at which the universe is expanding today. Pinpointing its exact value is like having the master key to the cosmos' size, age, and ultimate fate. For decades, we've had two primary and seemingly foolproof methods for measuring it. The first is the distance ladder method, which uses the predictable brightness of certain stars and supernovae as standard candles to measure distances to relatively nearby galaxies, building a step-by-step ladder out into the cosmos. This method, painstakingly refined over years, gives us one very precise number for the expansion rate. The second method looks back to the very beginning. By exquisitely mapping the faint irregularities in the cosmic microwave background, the afterglow of the Big Bang, we can use our robust theory of the universe's evolution to predict what the expansion rate should be today. This is a pristine, early universe measurement. The problem, these two methods, each performed with incredible precision, do not agree. They are decisively, undeniably different. It's as if you used two different, perfectly calibrated rulers to measure the same table and got two consistently different answers. The early universe method suggests a slower expansion rate, while the local universe method insists it's faster. The gap between them is not a small error. It is a significant and growing discrepancy that has withstood intense scrutiny. This is the Hubble tension. And its persistence suggests that our standard model of cosmology, the wonderfully successful lambda CDM model that incorporates dark energy and cold dark matter, might be incomplete. Could dark matter hold the key? Perhaps dark matter isn't entirely cold. Maybe a fraction of it interacts with itself or with dark energy in a way we haven't accounted for, subtly altering the expansion history of the universe between its primordial epoch and the present day. Or perhaps the properties of dark energy are not constant, but evolving. This tension is more than a statistical glitch. It is a direct challenge, a signal from the cosmos that our understanding of its fundamental components, especially the dark ones, is still lacking a crucial piece. If the Hubble tension questions the uniformity of the universe's expansion in time, the next mystery questions its uniformity in space. It's a finding so strange that cosmologists half-jokingly named it the axis of evil. This mystery also comes from the cosmic microwave background, but instead of looking at the tiny temperature differences, it concerns their alignment, or lack thereof. According to our foundational cosmological principle, the universe should have no preferred direction. It should be isotropic, looking the same in every direction. The patterns in the CMB should be completely random, but they are not. When scientists analyzed the data from the Planck satellite and other missions, they found that the larger scale fluctuations in the microwave background appear to be subtly aligned along a particular axis that stretches across the sky. Some of the largest warm and cool spots seem to line up in a way that defies the odds, a clustering of anomalies that suggests a directionality to the universe. This axis is the axis of evil, a nickname reflecting how deeply unsettling this finding is to our standard models. What could possibly cause such a preferred direction? One tantalizing possibility is that it's an imprint of the dark matter web itself. We know the cosmic web is not a perfectly symmetrical sphere. It is an intricate, lopsided structure with long filaments and great walls. Perhaps the gravitational pull of an immense, unseen superstructure beyond our observable horizon, a vast concentration of dark matter, is tugging on our entire local universe, creating a dip in spacetime that leaves this strange directional mark on the oldest light we can see. It would be a cosmic wake, evidence that even on the grandest scales, the distribution of dark matter is not perfectly even, and its gravity can define a true north in the cosmos. Both the Hubble tension and the axis of evil are profound puzzles, reminding us that for all our knowledge, the dark universe still has the power to surprise and humble us. While the Hubble tension and the axis of evil challenge our view of the universe's large-scale structure and expansion, some of the most compelling evidence for dark matter's influence comes from the very beginning of everything, from a process that forged the first atomic nuclei. This is Big Bang nucleosynthesis, the epoch in the first few minutes of the cosmos, when the universe was a blazingly hot fusion reactor, cooking the primordial elements. The predictions from this theory are spectacularly accurate for the most part. The calculated abundances of helium and deuterium match what we observe in the oldest, most pristine regions of space with near-perfect precision. It is one of the cornerstones of the Big Bang model, but there is one glaring, persistent exception: lithium. The standard model of nucleosynthesis predicts a certain amount of lithium-7 should have been created in that primordial forge. Yet, when astronomers measure the lithium abundance in the ancient atmospheres of the oldest stars, in the halo of our galaxy, stars that formed from that untouched primordial gas, they find only about a third of the expected amount. This is not a small miscalculation. It's a discrepancy by a factor of 3, and it has stubbornly resisted explanation for decades. It's known simply as the cosmological lithium problem. So where did the lithium go? Or perhaps, was it never made in the expected amounts to begin with? This is where dark matter offers a tantalizing solution. What if the calculations are correct, but our model of the early universe is missing a key ingredient? Some theorists propose that certain types of dark matter could have been present and active during those first critical minutes. For instance, if a fraction of dark matter particles were unstable and decayed during nucleosynthesis, they could have injected additional energy into the primordial soup. This extra energy would have disrupted the delicate chain of nuclear reactions, perhaps by breaking apart the fragile beryllium nucleus that is a crucial stepping stone in the creation of lithium, effectively shutting down the production line. Alternatively, if dark matter particles interacted with protons and neutrons through a force other than gravity, they could have altered the reaction rates themselves, leading to a different end result. The lithium problem is a tiny, specific anomaly, but like a single wrong note in a symphony, it points to a potential flaw in the entire composition, suggesting that the invisible hand of dark matter was at work even before the first stars were born. Solving a puzzle from the universe's first minutes is one thing, but the ultimate challenge is far grander, weaving dark matter into the very fabric of physics itself. For all its gravitational might, dark matter remains a profound outlier, a glaring exception that the two most successful theories in scientific history cannot explain. On one hand, we have the standard model of particle physics, a masterpiece of human ingenuity that describes with incredible accuracy the zoo of subatomic particles and 3 of the 4 fundamental forces. It has predicted the existence of particles like the Higgs boson with stunning precision, yet it has no place for dark matter. There is no particle in its inventory that fits the bill. On the other hand, we have Einstein's theory of general relativity, our magnificent description of gravity, space-time, and the cosmos on the largest scales. It predicts black holes, the bending of light, and the expansion of the universe. It is the framework we use to map the dark matter web through gravitational lensing. But here's the profound irony. General relativity tells us dark matter must exist because of its gravitational effects, but the theory itself is completely silent on what dark matter actually is. It describes the force, not the source. This is the great divide. We have a theory that brilliantly explains the very small, and a theory that brilliantly explains the very large, and they are fundamentally incompatible when it comes to this one critical component that makes up 85% of the universe's matter. Unifying them into a single, coherent framework that naturally incorporates dark matter is the holy grail of modern physics. The quest for this unified theory has led us to some of the most fascinating ideas in science, from supersymmetry and extra dimensions to the possibility that our gravity is leaking into other universes. Yet, each potential solution brings its own immense complexities, and so far, a lack of experimental confirmation. The core of the problem is that dark matter exists at this uncomfortable intersection. It is a particle-like entity that must be explained by a new particle beyond the standard model, but its primary and most obvious effect is gravitational, the domain of general relativity. Until we can find a way to make these two worlds speak the same language, dark matter will remain the ghost in the machine, the universe's greatest unsolved equation, a constant reminder of how much we have yet to learn about the true nature of reality. If our own Milky Way seems to be missing its entourage of small, dark satellites, then the discovery of a completely different class of ghostly galaxies presents us with a mystery that is somehow even more bizarre. For decades, our understanding was simple. A galaxy's size and brightness were a direct reflection of its mass. A giant, brilliant spiral galaxy must be anchored by a massive halo of dark matter, while a small, faint dwarf galaxy would be held together by a much smaller one. It was a tidy, predictable relationship, but the universe, it seems, delights in breaking its own rules. Enter the ultra-diffuse galaxies and their most famous enigma, Dragonfly 44. Discovered lurking in the Coma cluster, Dragonfly 44 is a galaxy that defies all conventional logic. To the eye, it is a spectacular failure. It is as large as our own Milky Way, stretching across a similar vast expanse of space, but it contains almost none of the stars. Where our galaxy blazes with hundreds of billions of stars, Dragonfly 44 has just 1% of that number. It is a ghostly haze, a wisp of starlight so faint that it was only recently detected with specially designed telescopes that filter out scattered light. It is the cosmic equivalent of a balloon inflated to the size of a hot air balloon, but containing only a single breath of air. You would naturally assume such a faint, failed object must be incredibly lightweight, a featherweight in the cosmic arena. But when astronomers measured the velocities of its few stars, they got a shock. Those stars were moving at tremendous speeds, orbiting the galaxy's center so fast that, according to the laws of gravity, they should have instantly flown off into intergalactic space. The only thing that could possibly be holding them in such a tight, rapid orbit is an immense amount of mass creating a powerful gravitational field. The math revealed a staggering truth. Despite its phantom-like appearance, Dragonfly 44 possesses a dark matter halo of colossal proportions, with a mass nearly 1 trillion times that of our Sun. This galaxy is 99.99% dark matter. It is not a failed galaxy. It is a dark matter galaxy that just happens to have a few stars sprinkled on top. It is a pure, almost uncontaminated specimen of the cosmic web's underlying architecture, made visible. How does such a thing form? The leading theory is one of galactic robbery. Dragonfly 44 lives in a dense, violent environment, the Coma Cluster, a crowded metropolis of galaxies constantly interacting. It's possible it was once a more typical galaxy, but as it orbited through the cluster, its gas and stars were brutally stripped away by the gravitational tides of larger neighbors, like a smaller fish being picked clean by sharks. What remained was its dark matter core, which is immune to this stripping because it doesn't interact, leaving behind a massive, dark skeleton. Alternatively, these galaxies could be ancient relics, forming in patches of the early universe that were so dense with dark matter yet so devoid of the normal gas needed to form stars that they simply never got going. They are the cosmic equivalent of a powerful engine that never got any fuel, but the influence of this dark architecture may extend far beyond creating these strange, isolated phantom galaxies. There is growing evidence that the dark matter web doesn't just provide a passive scaffold. It may actively guide the destiny of the galaxies within it, like a phantom hand shaping cosmic evolution. One of the most puzzling pieces of evidence for this is a phenomenon known as galactic spin alignment. When a spiral galaxy forms, the direction in which it spins, whether its arms are rotating clockwise or counterclockwise from our perspective, should be essentially random, determined by local, chaotic conditions during its collapse. There is no reason for the spins of galaxies separated by vast distances to be coordinated in any way. Yet, that is precisely what some astronomical surveys are suggesting. Observations have shown that the spin axes of spiral galaxies millions of light years apart appear to be correlated with the large-scale filaments of the cosmic web they are embedded in. Galaxies within the same vast filament seem to show a preference for rotating in a direction that is aligned with the filament's axis, as if they are all spinning like balls, rolling down the same invisible cosmic highway. This is not something that gravity alone can easily explain. The gravitational pull from the filament is far too weak and diffuse to orchestrate the detailed angular momentum of countless galaxies. This points to a more profound and subtle influence. The dark matter web is not a static structure. It is dynamic, with streams of dark matter constantly flowing along these filaments, funneling into the waiting gravitational wells of galaxy clusters. It's possible that this streaming motion, this directional flow of the unseen substrate of the universe, imparts a subtle torque on the collapsing clouds of gas that eventually form galaxies. As a proto-galaxy condenses within a filament, this cosmic current could guide its spin, setting it in motion like a leaf caught in a river's flow, aligning it with the grand architecture of the web itself. This phantom hand of dark matter would therefore not only build the cosmic cities, but also influence the very dynamics of the inhabitants, a hidden director orchestrating the ballet of the galaxies from the shadows. Looking back across 13.8 billion years, we arrive at the very beginning to a question that has no easy answer. when and how was dark matter born? Its origins are shrouded in the intense heat and density of the very early universe, a realm where our known physics begins to break down. We know it must have been created somehow, as all matter was, but the mechanism remains one of the deepest puzzles. The leading theories take us into incredibly exotic territory, proposing creation stories that are as fascinating as they are difficult to test. The most widely accepted idea is known as thermal production. In the unimaginably hot and dense first moments after the Big Bang, the universe was a seething soup of energy and every kind of particle and antiparticle, all constantly colliding and annihilating each other. In this frenzy, dark matter particles would have been continuously created and destroyed, maintaining a state of thermal equilibrium with everything else. But as the universe expanded and cooled at a furious rate, a critical moment arrived. The temperature dropped below the mass energy required to create new dark matter particles. The frequent collisions stopped. The existing dark matter particles could no longer find partners to annihilate with, and they suddenly found themselves frozen out of the thermal bath, a relic population left drifting in the expanding cosmos. This process, called thermal freeze-out, is beautifully elegant. The final abundance of dark matter it predicts depends almost entirely on one property: how strongly the dark matter particles interact with normal matter. The weaker the interaction, the later they freeze out, and the more of them are left behind. For the popular WIMP candidate, this predicted abundance aligns miraculously with what we observe today, the so-called WIMP miracle that has driven decades of research. But the universe may not be so simple. Other, more dramatic birth scenarios are possible. In non-thermal production, dark matter wasn't cooked in the general heat of the Big Bang, but was forged in specific, violent events. Perhaps it was created during cosmic phase transitions, moments when the fundamental forces of nature split from one another, releasing immense energy like cracks forming in freezing ice. Or maybe dark matter particles are the remnants of decaying heavier objects from the early universe, like cosmic fossils. Another radical idea proposes that dark matter wasn't created from energy at all, but was instead generated by the gravitational field itself in a process called gravitational particle production. In the violent, inflationary expansion of the universe just after the Big Bang, the fabric of spacetime was shaking and flexing violently. This shaking could have been so intense that it literally shook loose pairs of particles from the vacuum of empty space itself. In this scenario, dark matter is a direct echo of spacetime's first tremors, a ghostly residue of creation born from the geometry of the cosmos. Whenever and however it was born, this nascent dark matter didn't remain idle. Its gravitational pull immediately went to work, beginning the single most important construction project in history, building the cosmic web. And to see the first fruits of that labor, we must travel forward in time to a period cosmologists call the Cosmic Dawn. This was the end of the universe's dark ages, a several hundred million year stretch of profound blackness after the glow of the Big Bang had faded to cool microwave radiation, and before the first stars had switched on. During this time, the dark matter web had already formed its vast, invisible skeleton. In the deepest gravitational wells at the intersections of filaments, the first clumps of normal matter hydrogen and helium gas were slowly, inexorably being gathered. Then it happened. Within these dense pockets of gas, held firmly in the grip of dark matter's gravity, the first protostars began to condense. They were not like the stars of today. They were behemoths, hundreds of times more massive than our sun, burning ferociously hot and bright with pure hydrogen fuel. Their ultraviolet radiation blasted out into the surrounding darkness, and in doing so, they began to fundamentally change the nature of the universe itself. This radiation started to rip apart the neutral hydrogen atoms that filled all of space, exciting them and knocking their electrons loose in a process called reionization. The universe was slowly being transformed from a neutral, opaque fog into the transparent, ionized plasma that fills intergalactic space today. We are now on the cusp of directly witnessing this epic dawn. The key to seeing it lies in a faint whisper of radiostatic, a specific signature from neutral hydrogen known as the 21-centimeter line. Hydrogen atoms occasionally emit a tiny amount of energy at a wavelength of 21 centimeters. By building enormous, exquisitely sensitive radio telescopes like the Square Kilometer Array, astronomers are essentially building a time machine to tune into this signal from the universe's infancy. The pattern of this signal across the sky will be a direct map of the distribution of that primordial neutral gas, and since that gas was shaped exclusively by the gravitational pull of the dark matter web, this map will also be a precise tracing of the dark matter skeleton at its most pristine state. Even more intriguingly, the characteristics of this signal could reveal dark matter's properties in a way nothing else can. If certain types of dark matter particles interacted with this hydrogen gas, even slightly, they would have subtly warmed it or altered its distribution. This interaction would leave a distinct imprint on the 21-centimeter signal, a unique fingerprint in the radio waves. By listening to the echoes of the first light, we may finally hear the faint signature of the dark matter that made that light possible, uncovering not just the structure of the first cosmic web, but the very nature of the material from which it was spun. But if mapping the first light offers a glimpse into dark matter's primordial influence, our next mysteries force us to consider its potential relationship with the other great cosmic unknown, and to ask a question that verges on the philosophical. We've explored dark matter and dark energy as separate entities, one pulling the cosmos together with gravity, the other pushing it apart with its mysterious repulsive force. They seem to act in opposition, one shaping structure, the other dissolving it. But what if they are not independent? What if these two shadowy giants are somehow connected, whispering to each other across the vast expanses of space and time? This is the provocative idea of dark matter-dark energy coupling. In our standard model of cosmology, lambda CDM, these two components are treated as entirely separate. The lambda represents dark energy, assumed to be a constant force inherent to the vacuum of space itself. The CDM stands for cold dark matter, particles that simply gravitate. They don't interact, they just coexist, their effects playing out independently on the cosmic stage. Yet, several of the puzzles we've encountered, the Hubble tension, the unexpected properties of dwarf galaxies, hint that this simple picture might be incomplete. What if dark energy isn't constant? What if its strength has evolved over the history of the universe? And what if that evolution is tied to the behavior of dark matter? This is the core of the coupling hypothesis. It proposes that dark energy, the force driving expansion, could actually be draining energy from dark matter itself. Imagine dark matter as a vast reservoir of latent energy, frozen in the mass of its particles. A coupling theory suggests that this energy could be slowly converting into the repulsive force of dark energy, causing the acceleration of the universe to increase over time. It's a cosmic transfer of power, where the energy for the expansion is siphoned from the invisible matter that fills space. Alternatively, this interaction could work the other way, with dark energy influencing how dark matter clumps together, potentially explaining why we see fewer small galaxies than our simulations predict. While still highly speculative, this idea demonstrates a key truth in cosmology. When two components make up 95% of everything in the universe, assuming they have nothing to do with each other might be the biggest assumption of all. This line of thinking pushes at the very boundaries of physical theory, but our final mystery takes a step even further, into a realm that challenges not just our understanding of physics, but the nature of reality itself. The cosmic web, with its intricate, almost computational precision, has inspired a startlingly speculative question: could our universe be a simulation? The argument, in its simplest form, points to the universe's deeply mathematical nature. The laws of physics operate with unwavering consistency, like the unchanging code of a perfectly programmed system. The large-scale structure of the cosmos, with its fractal-like filaments and nodes, bears a striking resemblance to the neural networks of a brain or the distribution of processing power in a vast, interconnected supercomputer. Proponents ask, is this elegant mathematical architecture a hint of an underlying computational reality? From a scientific standpoint, this idea is currently untestable and therefore sits outside the realm of traditional science. There is no experiment we can yet devise to prove or disprove it. However, it serves as a powerful philosophical mirror, reflecting our own technological evolution. As we create increasingly complex virtual worlds ourselves, the question arises: if a conscious being in one of our simulations began to question its own reality, what clues would it look for? Perhaps it would search for the resolution limits of its universe, tiny, pixel-like grains in the fabric of spacetime. Some scientists have seriously proposed looking for such artifacts, like anomalies in the directions of ultra-high-energy cosmic rays that might hint at an underlying lattice structure to space, a signature of a finite computing system. While no such evidence exists, the very act of looking is a testament to the profound mystery we face. The cosmic web, this magnificent dark matter skeleton, is either the natural outcome of impersonal physical laws operating on a random quantum fluctuation, or it is the visible expression of a logic and structure we can scarcely comprehend. In either case, its existence compels us to look deeper, to question further, and to remain humble in the face of a universe that is far stranger and perhaps far more ingeniously constructed than we ever imagined. The idea that our universe's dark matter web might be a cosmic fingerprint from a reality beyond our own is a concept that pushes the boundaries of physics into the realm of the extraordinary. This brings us to a mystery that ties the largest structures we know to the possibility of the largest of all ideas, the multiverse. The concept of a multiverse suggests our cosmos is just one of many universes, each with its own unique set of physical laws and constants. In some, gravity might be stronger. In others, the weak nuclear force might not exist at all. Most of these universes would likely be stillborn or chaotic, incapable of forming atoms, stars, or life. Ours, however, appears to be finely tuned. The strength of gravity, the mass of a proton, the exact energy state of the vacuum, all these values seem precisely calibrated to allow for a stable, long-lived universe that can generate complex structures. This is the anthropic principle, and the dark matter web is a central character in this story. Consider the specific density of dark matter. What if it wasn't the value we observe? If there were significantly more dark matter, its intense gravitational pull would have caused the universe to collapse back on itself in a big crunch long before galaxies could ever form. If there were significantly less, gravity wouldn't have been strong enough to amplify those initial tiny fluctuations. There would be no cosmic web, no galaxy clusters, no stars, and no planets. Just a thin, expanding haze of gas forever. The fact that we have just the right amount of dark matter to sculpt the grand web we see, without destroying everything, is a staggering coincidence. One compelling resolution to this coincidence is that our universe isn't special. It's just one of countless possibilities where the numbers randomly worked out. In this vast multiverse, we naturally find ourselves in a universe where the dark matter density is perfect for web formation, because that's the only kind of universe that can support beings to observe it. The intricate filaments and nodes we map through gravitational lensing could therefore be more than just a structure. They could be direct evidence of our universe's specific address in a far vaster multiversal landscape, a unique signature of our particular set of physical laws. But if the web connects us to other universes, it also presents a profound puzzle about information within our own, leading to one of the most theoretical and mind-bending mysteries in all of physics. This is the potential connection between the cosmic web and the black hole information paradox. At first glance, a vast, invisible network and a super-dense point of gravity seem unrelated. But they are both connected by a fundamental question: what happens to information? In physics, information is not just data. It's the complete set of properties that defines every particle, its mass, its spin, its position. The laws of quantum mechanics state that information cannot be created or destroyed. It can only be transformed. This is a bedrock principle. However, black holes violently challenge this. If you throw an encyclopedia into a black hole, the black hole's mass increases slightly, but according to Stephen Hawking's work, it evaporates over astronomical timescales by emitting Hawking radiation, which is random and featureless. The information contained in that encyclopedia appears to be utterly lost, erased from reality, which violates quantum mechanics. This is the information paradox. Now let's scale this up. From a single black hole to the entire cosmos, the universe is often described as having a horizon as well, the limit of what we can ever observe due to the finite speed of light and the acceleration of expansion. What happens to the information of particles that cross this cosmic horizon? They are lost to us forever, just like matter falling into a black hole. Some physicists, inspired by the holographic principle, which suggests that all the information within a volume of space can be encoded on its boundary, have proposed a radical idea. Could the dark matter web be involved in this cosmic scale information processing? The web is the ultimate repository of mass in the universe, and its specific structure, the exact arrangement of every filament and void, contains an immense amount of information about the initial conditions of the Big Bang and everything that has happened since. It's a gravitational fossil record of unparalleled detail. One speculative theory suggests that the information of particles that become lost beyond the cosmic horizon might not vanish, but could somehow be imprinted or reflected in the properties of the dark matter web within our observable universe. In this view, the web isn't just a structure, it's a dynamic storage medium, a cosmic hard drive maintaining the universe's informational balance. While this remains a highly speculative and mathematically complex idea, it highlights how the greatest mysteries of the very small, like the fate of quantum information, might be inextricably linked to the greatest mysteries of the very large, with the dark matter web acting as the mysterious bridge between them. Peering billions, even trillions of years into the future, the ultimate fate of the cosmic web is inextricably tied to the mysterious force we call dark energy. Right now, we exist in a cosmic sweet spot, a golden age for structure. Gravity has spent billions of years patiently constructing the dark matter filaments and clusters, and dark energy has only recently begun to dominate, starting its campaign of accelerated expansion. But this is a battle with a foregone conclusion, and the outcome hinges on the true, unknown nature of dark energy itself. One possible destiny is a slow, inexorable dissolution. If dark energy behaves as a constant force, as our simplest models suggest, its repulsive push will continue to grow stronger as the universe expands. Over unimaginable eons, the expansion will accelerate faster and faster. The vast voids between the filaments of the web will stretch and grow, becoming ever more empty. The gravitational ties that bind galaxy clusters together will be stretched beyond their limits. First, the large-scale connections between superclusters will snap. Then, individual galaxy clusters themselves will be pulled apart. Eventually, even individual galaxies will be isolated, their stars drifting apart into the growing darkness. The universe will become a cold, ever-thinning soup of isolated stars and dark matter clumps, each receding from the others faster and faster, leading to a frozen, lonely end known as the heat death. But there is a more dramatic and terrifying alternative, the Big Rip. This scenario arises if dark energy is not constant, but instead grows stronger over time. In this model, the repulsive force would eventually become infinite. The acceleration wouldn't just empty out space, it would tear the very fabric of spacetime itself. As the end approaches, the force would overcome the gravity holding our own Milky Way together, shredding it into individual stars. Then, it would grow stronger still, overcoming the forces holding those stars together, ripping them apart in a final, violent cataclysm. Ultimately, even atoms, nuclei, and the fundamental particles that make up all matter would be torn asunder. The cosmic web, the grandest structure in existence, would be violently unraveled down to its most fundamental threads, leaving behind a void of nothingness. The choice between a frozen eternity and a violent end rests entirely on the unknown properties of dark energy, a reminder that the fate of everything is written in the dark. This brings us to the final, and perhaps most profound, question of all. Could we be completely mistaken, after decades of searching, with no direct detection of a dark matter particle? A small but persistent group of scientists continues to ask if the entire paradigm is a colossal error in our thinking. They propose that instead of invoking an invisible substance, we should consider that our understanding of gravity itself is incomplete. The leading alternative is known as modified Newtonian dynamics, or MN. It proposes that on very large scales, or in regions of extremely weak gravity, the force of gravity doesn't behave as Newton or Einstein predicted. It becomes slightly stronger. This modification could potentially explain the flat rotation curves of galaxies without needing extra mass, the anomaly that started this whole quest. For a single, isolated galaxy, MIND can work surprisingly well, but the cosmic web presents a challenge of an entirely different magnitude. Can a modification of gravity explain the intricate, vast network of filaments and voids we see mapped through gravitational lensing? Can it account for the detailed separation of mass from visible gas we witnessed in the bullet cluster? The evidence for dark matter is no longer just about galaxies spinning too fast. It's woven into the large-scale structure of the entire universe. While some researchers are developing more sophisticated relativistic versions of MIND to try and tackle these challenges, they often have to introduce new, exotic fields that begin to look philosophically similar to dark matter itself. The grand mystery of the cosmic web, with its specific gravitational fingerprints, remains the most significant hurdle for any alternative theory. It forces us to confront a humbling possibility that our intuition, built on the physics of the visible world, is simply inadequate to describe the true, dark reality of the cosmos. Whether the answer is an unknown particle or a revised law of physics, the journey to solve it continues to redefine our place in the universe. Recent breakthroughs in observational astronomy have given this invisible architecture a stunning, almost tangible form. For the first time, we are not just inferring the cosmic web, we are mapping it in meticulous, three-dimensional detail. Massive sky surveys, like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument, have undertaken the monumental task of measuring the precise positions and distances of millions upon millions of galaxies. This isn't just a cosmic census, it's the creation of the most ambitious atlas of the universe ever attempted. When you plot these galaxies in three-dimensional space, the result is breathtaking. What emerges is not a random scattering of points, but a delicate, intricate, and vast network, a cosmic spiderweb spun on a scale so grand it defies human comprehension. The sheer scale of these structures is almost impossible to grasp. The filaments themselves are not mere threads. They are colossal rivers of dark matter, often stretching for hundreds of millions of light years across the void. They form the dense superhighways of the cosmos, and at their intersections, they pile up into the most massive gravitationally bound structures in existence, galaxy clusters, which can contain thousands of galaxies all swarming together. Surrounding this luminous web are the great cosmic voids, unimaginably vast spherical regions of near total emptiness that can span over 100 million light years. This detailed map reveals a universe that is overwhelmingly empty, with all visible matter concentrated into a tiny fraction of space, tracing the lines of the dominant, unseen dark matter foundation. But scientists go far beyond simply admiring this cosmic cartography. They subject it to a rigorous mathematical interrogation to decode its deepest secrets. The primary tool for this is something called the power spectrum. In essence, this is a statistical method that quantifies the web structure. It measures how matter, both dark and visible, is clustered at different scales. Is the universe lumpy on large scales but smooth on small ones? Or is it the other way around? The precise shape of this power spectrum graph is like a unique fingerprint, and it holds incredibly precise information about the universe's ingredients and its history. By comparing the observed power spectrum from these galaxy surveys against the predictions of supercomputer simulations, cosmologists can perform a kind of cosmic autopsy. The specific lumpiness of the web, the exact sizes of the voids, the thickness of the filaments, all of these properties are exquisitely sensitive to the amount of dark matter, the nature of dark energy, and even the specific properties of the dark matter particles themselves. For instance, if dark matter were warm, meaning its particles were lighter and moved at higher speeds in the early universe, it would have prevented the formation of very small-scale structures. The power spectrum would show a lack of clumpiness on those smaller scales. The fact that our observed maps match the predictions for cold, dark matter so well is a powerful confirmation of that model. Every new, more detailed map from instruments like Daisy tightens the constraints further, narrowing down the possible identities of dark matter and bringing us closer to understanding the true blueprint of all existence. While the grand maps of the cosmic web chart the architecture of the invisible, the ultimate prize remains to touch the architect, to capture a single particle of dark matter, and finally bring it out of the shadows. This is the driving force behind a global, multi-pronged scientific assault, a quest that takes us from the depths of the Earth to the frontiers of space, all in pursuit of nature's most elusive substance. Deep beneath the surface, in abandoned gold mines and under mountains, lies our first line of attack. Here, shielded from the constant rain of cosmic rays that would drown out any faint signal, are the most sensitive detectors ever built. Experiments like LUX Zeppelin, or LZ, in South Dakota and Xenon T in Italy operate on a deceptively simple principle: weight. They consist of massive vats of ultra-pure liquid xenon, a dense noble gas surrounded by layers of shielding and sensitive light sensors. The concept is to wait for the incredibly rare moment when a weakly interacting massive particle, a WIMP, passing through the Earth actually bumps into the nucleus of a xenon atom. That tiny collision would produce two telltale signatures: a quick flash of light and a subsequent shower of electrons, creating a second burst. The job of these experiments is to sit in profound silence and darkness, listening for that unique double click, the signature of a ghost making contact. The engineering challenges are immense. The xenon must be purified to an unimaginable degree, free of any natural radioactivity that could mimic a dark matter event. The sensors must be exquisitely sensitive, and the entire apparatus must be protected from vibrations and background radiation. These are cathedrals of stillness, monuments to human patience, built to detect a whisper in a universe of noise. But if direct detection is like trying to catch a single, specific fish in a vast, dark ocean, then indirect detection is like looking for the ripples it leaves behind. This strategy involves scanning the skies for the secondary products created when dark matter particles annihilate or decay. The theory is that in regions where dark matter is exceptionally dense, like the centers of galaxies or within the filaments of the cosmic web, these particles might occasionally collide and destroy each other, converting their mass into a burst of energy and a shower of familiar particles we can see. This is where space telescopes become our eyes. The Fermi Gamma Ray Space Telescope tirelessly scans the heavens, searching for an unexplained excess of high-energy gamma rays, the telltale flash of light from such an annihilation event. It's particularly focused on dwarf spheroidal galaxies orbiting the Milky Way, as these are believed to be almost pure concentrations of dark matter, with very few conventional astrophysical sources that could confuse the signal. The James Webb Space Telescope joins this hunt with a different strategy. By peering into the earliest epochs of the universe, it can study the formation of the first galaxies. Their size, shape, and distribution are sculpted by the gravitational pull of the dark matter they formed within. If dark matter has specific properties, if it's warm or interacts with itself, it would have left a distinct imprint on these primordial structures. JWST is essentially reading the fossil record, looking for clues in the ancient light that point to the nature of the hidden material that guided its creation. And then there are particle colliders, like the Large Hadron Collider at CERN. This approach is the most direct of all. If we can't find dark matter in nature, we will try to create it. By smashing protons together at nearly the speed of light, the LHC recreates the intense energies of the early universe. The goal is to produce a pair of dark matter particles in the collision. We wouldn't see them directly in the detectors, as they would escape without a trace, but their presence would be inferred by a telltale energy imbalance, a measurable amount of momentum that seems to vanish from the collision, carried away by the invisible particles. Each of these methods is a cornerstone of the search, a different path up the same mountain, any one of which could lead to the discovery that rewrites our understanding of the cosmos. We have ventured from the faint whispers of gravity in spinning galaxies to the staggering possibility that our entire reality might be an intricate simulation. We have stood before the cosmic voids and traced the outlines of the invisible filaments that bind the universe together. Each of these 25 mysteries is a profound reminder that the cosmos is far stranger and more wonderful than we could have ever imagined, with dark matter as its silent, enigmatic architect. This journey doesn't represent a failure of our understanding, but rather a celebration of it, a testament to our relentless curiosity and our ability to piece together the secrets of the dark, even when we cannot see it directly. The most thrilling part of this story is that it is still being written. Every unanswered question, every unresolved tension is not a closed door, but an open pathway. It is an invitation for the next generation of thinkers, for the young person watching this right now who will one day design an experiment that finally captures a dark matter particle, or who will write a new equation that beautifully unites gravity with the quantum world. The mysteries of the cosmic web are beacons, guiding the telescopes of tomorrow and inspiring the theories that will reshape our place in the cosmos. Our map of the universe is still filled with blank spaces, and that is the most exciting thing of all. Now we turn to you. Which of these cosmic riddles captures your imagination the most? Does the eerie silence from deep underground detectors intrigue you? Or does the grand, philosophical scale of the multiverse stir your wonder? Share your thoughts in the comments below. We love hearing what sparks curiosity in our community. If you enjoyed this deep dive into the universe's greatest secrets, hit the like button to let us know. And subscribe to the channel, because this journey is far from over. We will be right here with you, exploring the next great discovery as we continue to unravel the mysteries of the cosmos.